loosely say broken ergodism. Yeah. What kind of a? Anything at all, any measurable set. Any set which has a finite volume, if you like. I'm saying that it's guaranteed to. If this happens, if this is so, then strong mixing occurs. That measure need not be. No, normally one would set mu of omega to be equal to 1 by saying that, look, the full volume element, let me test in phase space, let me normalize to 1. So one would set mu of omega to be equal to 1, in which case mu of A is a fraction. Yeah, that's what I'm assuming. I'm assuming you're talking about measurable sets everywhere. Yeah. You choose B, definitely. You shouldn't choose B in A at all. You should choose somewhere else. I put the drop of rum here and I choose this reference window. But I wait long enough, some of this rum is going to mix into this. Yeah.
If we choose a volume of B to be very small, such that A and intersection B becomes...
That's why I said measurable set. If I choose one point or a set of finite points, then the answer is 0. If you do not have periodic motion at all in a dynamical system, you don't have periodic motion at all, no point ever comes back to itself, then if you ask what's the probability or what's the measure of that particular point in phase space, the initial point, the answer is 0. That's the whole point. Always start with measurable sets. We will in fact see that in all our examples of chaos, there will be sets of measure 0 in the phase space for which you don't have chaos. But they are necessary because they will act as separatists. You have a point here which will be part of an unstable periodic orbit. Points infinitesimally to the left and right will throw this phase space point away from itself in both directions. That's how chaos occurs. That's the subtle way in which chaos occurs. But you do need this set of unstable periodic orbits, regular motion. They have to be all unstable, otherwise things would fall into it. And you need a dense set of it everywhere. And we'll see how this magic appears by which you have dense sets of unstable periodic orbits in a continuum. So a little bit of measure, subtleties of measure is involved. So I said that the next thing would be to have exponential separation. Exponential or instability. Now this exponential separation could be in any direction whatsoever in phase space. There must be at least one direction in which it is exponentially separated. Moreover, you could say, oh, how do I know? Portions which started here may separate very slowly, portions which started here may separate very fast, etc. So exponential separation on the average over phase space. That's the weaker form. So on the average. Not everywhere, but on the average. You average over all of phase space. You take this initial set A to be everywhere in phase space, one after the other, and you discover if globally, on the average, you have exponential separation of nearby trajectories, then I say this system is exponentially unstable.
So if you have a system on a very high order tori,
yes.
So there the average has to be taken over the whole phase space or the high order tori?
Once you have a torus, then on that torus, if it's quasi-periodic motion, and we're talking about a Hamiltonian system, the motion is not exponentially separating. How is it separating? You already know it. How is it separating? Remember the theta i's we solved, and there were theta i's, theta 0 plus t. So the separation on the torus will only be linear. Guaranteed for an integrable system. Can never be exponential. So you're automatically not on any torus. Gone well beyond all. Such a system, exponential system on the average, is called a K system. A Kolmogorov system. And I'm going to give examples and we'll see how this works. Then, next in order of complexity. Oh, by the way, a K system implies this. So, This is not implied, but that is implied. Of course. It's mixing and it's exponentially rapidly mixing. The next in complexity is not in the average, but everywhere, except for sets of measure 0. So, globally, exponentially mixing. And of course, that will imply that, but this does not imply this. This is an extremely unstable system. Wherever you start, except for sets of measure 0, except for isolated points whose measure is 0, they could exist, they will always exist, but whose measure is 0. And then you have systems beyond this which are as random as a coin toss in a very specific way, totally random systems. Deterministic dynamics, but the dynamics is so complex that it is essentially completely random as a coin toss in a very specific sense. And such systems are called C systems. Or Anosov systems. But this will imply that, won't imply this. Pardon me? Mixing does not, it could mix in a power law. This separation could always be like a power law. It could be diffusive mixing. It's not exponential. The separation between trajectories is not exponential.
These are kinds of mixing.
But these are kinds of mixing. These are kinds of mixing. And this one here is as random as a coin toss. Even if there's mixing, even if there's exponential instability, you could still have a certain amount of determinism left in the system, predictability left in the system, and you lose even that if there are certain conditions are satisfied. If, for example, you have hyperbolicity everywhere in the phase space, etc., no center manifolds and stuff like that, then you can have what's called a C system. Now, physical systems, most chaotic physical systems, would be somewhere here. These are some model systems, and so on. But most systems would be here. And if the perturbations in the system are sufficiently strong and there's not much determinism, not much regularity left, they could go here. Now, in the case of Hamiltonian systems, something special happens. You either have this or that, more generally this, and when you lose integrability, the system jumps here. But, well, not quite here. It jumps to a stage where you do not have power law mixing at all, but exponential mixing. In those regions where you have chaos. So it generally jumps here to this region, and after that, it jumps to this place exponentially, at least in some regions. And if the perturbation is sufficiently strong, the system is far away from integrability, then it goes to this in Hamiltonian systems. So that is why one says, unlike dissipative systems, when a Hamiltonian system becomes non-integrable, it means there exist initial conditions of non-zero measure which do not lie on tori, whose future doesn't lie on tori. At least some of the tori are destroyed, and you have some kind of exponential separation in some directions in phase space.
So in this case, separation is confined in a particular space.
Pardon me?
In this case, the separation is confined in some particular
Yeah.
space.
Now the question is, where is the separation confined, and how is it that when you have exponential separation, you can still have confinement to a particular point in phase region of phase space?
And also one question, may that represent some steady state?
Now the question is this happening in the steady state? The answer is yes, everything is in the steady state, asymptotically in the steady state, etc. Because I'm always taking that limit, n tending to infinity. So I'd like to know how this separation occurs, and does it settle down to something invariant, some distribution which is invariant. That's what is going to be our interest. Our basic interest in dynamical systems is, given a set of rules and a set of initial conditions, predict the future into arbitrarily long times. That's always our guideline. So for that, in chaotic systems, I need some invariant measure.
So you are talking about the Hamiltonian system is integral.
Yeah.
Then it has exponential separation.
Oh no, just the other way about it. No, just the other way about it. If it's integrable, then for the kind of motions we looked at, the motion occurs on an n-dimensional torus instead of all of 2 n-dimensional phase space. Every initial condition lies on a torus, maybe a different torus for different initial conditions, of course. Every initial condition lies on a torus, and on each given torus, 2 neighboring points will at best separate linearly in time. No more. So each of those conditions will be ergodic on that torus, but not in phase space. No ergodicity in general, no mixing, therefore none of the other ones.
So in chaotic systems,
Yeah.
you are saying that they are stochastic as well as deterministic, right? But the deterministic.
What's meant by stochastic?
When you said something, I don't get it.
Stochastic, I would like to reserve that word for a system which has elements of randomness or noise put in the evolution itself. I prescribe, I say, this term in the evolution equation is a random variable picked from some pre-assigned distribution. But I'm not doing anything like that. I give you a set of rules and that's completely deterministic. So I'd like to say chaotic rather than stochastic. But the behavior of elements of phase space could mimic random processes. Could certainly mimic random processes. I break up phase space into cells and look at all the initial conditions in a given cell and ask when do these conditions come back, when do they visit other places, when do they exit, and so on. I could map this question onto the behavior of a random process of certain kinds. Then I have stochasticity in that sense.
These C systems are basically stochastic.
Pardon me?
The C systems which you.
Yeah.
So they are basically.
No, they will be deterministic models, but they will display elements of exactly the same behavior as, for example, tossing a coin. We will see an example explicitly, and in what sense this is so. So it will lead us into a question of what the hell do I mean by randomness? There's no way of defining it, by the way. There's no way of defining what a random process is. There's no fully rigorous definition of what's a random variable. You have to put some axioms in and say this is what I define by a random variable. Otherwise, I don't know what a random process is. I give you a piece of music, it is very well known, I stop it at some particular point and I say this is a random process. Because unless I play the next note, you don't know whether it's a realization of a random process, a very rare realization which is so regular in the beginning and then after that it goes into noise. How do you know? Till I play the whole thing from t equal to minus infinity to plus infinity. There are several levels of randomness.
In simulations, we used to use random number generation.
Pardon me?
In the process of simulations, we use
Yeah.
random number
Yeah.
generation. And the process is deterministic, but we get
Yeah.
sequence of random
Exactly.
number. So is
Exactly.
that the C system?
Exactly. So in the process of random number generation, you use some deterministic algorithm, of course. And then you say it's random. I mean, you know, for example, when you press this RAN button in your old pocket calculators, which maybe this generation doesn't have, you get a 3-digit number between 0 and 1, and you go on pressing it and plot the histogram, and lo and behold, instead of a flat histogram, you get something that's beautifully wavy up and down. Because that damn thing has got a program where it's generating a random number based on the zeros of a Chebyshev polynomial of order 128. So that looks very random for a long time, but you do this till the battery runs out and you discover this beautiful curve. So it's not true random number generation. And I will talk about the Ulam map where they generated random numbers. That's one of the first examples where in the Second World War, in the Manhattan Project, Ulam and von Neumann generated 4-digit random numbers by using a deterministic map, which today we know as a logistic map. Okay. So it's in a very precise sense that we can quantize its, characterize its randomness. You'll see. Yeah. Pardon? Yes. It cannot. Yes. Hamiltonian systems cannot have attractors. Because any attractor means that you have a shrinkage of volume elements. It's not possible. Not possible. But you could still have chaos because you just keep wandering around without settling down. Yeah, it could have unstable fixed points, of course. But it cannot have nodes, it cannot have focus, spiral points. All those involve shrinkage of volume. So a Hamiltonian system, as far as its critical points are concerned, can have only saddle points and centers. It cannot have a limit cycle, because that's a stable limit cycle would be an attractor. It cannot have a limit cycle. But it could have other objects. It cannot have a stringed attractor, because even that implies shrinkage of volume. But it could be chaotic. Pardon me? Those are only in dissipative systems. So now let's go to models, because I want to show explicit calculations how this magic works. Yeah. Yeah.
Because partly like exponential is separated for some initial condition.
Right.
So there are also initial conditions which show some regular motion.
Yes, which will lie on tori, for example.
But is it the case that it's always the case that the measure of the initial conditions is separate exponentially is 1, even when there are regular motions?
No, let me give you an example. This is only a picture, but suppose you have one torus like this and another torus like that, and fellows who lie on this torus lie there, fellows on that torus lie there, and suppose in between there are no tori and there's a phase space point inside, it starts inside. That fellow will wander around irregularly in this inner region. It cannot cross this torus because phase trajectories cannot intersect. So it can never come to that torus or this inner torus, but it will wander around in between everywhere, and it could be chaotic in there.
So the volume of regular initial conditions is 0.
No, I'm not saying that at all. And it depends on the perturbation. So in a Hamiltonian system, which is integrable to start with, the measure of integrable initial conditions, regular motion, is 1, the full phase space. When it is globally chaotic, then the measure of initial conditions for which the motion is regular is 0. There could be isolated initial conditions, but the measure, volume is 0. And you have anything in between possible. Anything at all. So now we need to quantify this. Unfortunately, what happens is, in 3 dimensions, for chaos to occur, for exponential separation to occur, and so on, you can only have this in the case of differential equations in 3 variables at the very least. And I can't draw pictures with 3 variables. Moreover, by definition, such differential equations cannot be integrated. I can't reduce it to quadratures and integrate the whole thing and write a formula down, because then it cannot display chaos at all, because it becomes integrable. So one needs a model where I can solve, quote unquote, the system in reasonable completeness, and yet which displays chaos. And the answer has now been found that it lies in discrete dynamics. Instead of continuous time dynamics, you have discrete time dynamics, which is called maps, and they display these features, and we can then convert the information gained from those maps to continuum dynamics, to continuous time dynamics. For instance, in this torus motion which I talked about, quasi-periodic motion, one trick was to, instead of looking at the 2-dimensional motion, make a section of this torus and look at a discrete map on the circle. That was an example of a Poincare section which converted a smooth, continuous Hamiltonian flow into a Hamiltonian map. And that's the trick we're going to use. So now, from now on, I switch to discrete time and I say my time flows in discrete steps. So, yeah.
Maybe I missed why time is not continuous concept.
If time is continuous, in order to display chaos, I need at least 3 differential equations. In 2 differential equations, the phase space becomes a plane. And on a plane, phase trajectories for autonomous systems cannot intersect each other. And you cannot show display chaos at all. So you can rigorously show this. The only things you can have are fixed points, stable or unstable, and limit cycles. And the matter ends there. In neither of these cases do you have exponential sensitivity. But the moment you have 3 or more differential equations, there is exponential divergence possible, even in a bounded phase space, but I cannot write down solutions and show it to you. I can only do it numerically. Instead, if I want to do things analytically and exhibit to you what are the measures of chaos, etc., I need a system where I can make some calculations, where I can actually demonstrate to you how errors amplify exponentially. And that happens in discrete time systems. You could ask why in discrete time systems does this happen? I will explain in a minute. So I'm going to look at a system which is described by a variable x in discrete time. So because it's discrete, I'll use a subscript here and say that the deterministic rule that I'm giving, again, it's autonomous, is some nonlinear function of x. So there's a rule of evolution. This f is a nice smooth function. You know, assume all sorts of properties to it. It will turn out that I will allow f to be have cusps, it will have discontinuities, etc. I'll prescribe this f appropriately, and you will see the possibilities that occur. Now you could make this x itself a multi-dimensional object. The phase space could now be multi-dimensional. But the complexities that we want to look at already happen with one variable. Unlike the case of differential dynamics where you need at least 3 variables. But here with one variable I can therefore draw pictures. This thing already displays chaos if f is chosen appropriately in a very precise, well-defined sense. So I will use this. But you could have multi-dimensional maps, and they have not been very much explored except for n equal map dimensionality equal to 2 or 3 or something like that. It gets increasingly complicated to explore these things. Many, many possibilities occur. They have not all been catalogued. So my n will be time, discrete time. And this is some nonlinear function. Moreover, the interest will not be in letting this phase space x be infinite, because then things can wander off to infinity. That's not what I'm interested in. I'm interested specifically in systems where the phase space volume is bounded. So I will restrict x to some interval. Say this x is restricted to some interval, usually the unit interval or something like that. And the idea is to write this map down and ask what happens under iteration to these points. So I'll start with the initial condition in this interval and try to restrict it to this interval by changing the map appropriately. Otherwise you have escape to infinity, and there is a way of studying that too, but that's not our primary interest here. Now, in a nutshell, let me quote the result and then we look at the examples. I mentioned that for chaos to occur, by chaos I mean exponential separation of trajectories to occur, I mentioned you need at least 3 differential equations, 3 independent variables. In the case of discrete time dynamics, 1 is enough provided this map is not invertible. If this map is invertible, this one-to-one map, then this doesn't happen at all. The map cannot be invertible. In other words, if you give me xn minus 1, I plug it in this rule and I find an xn uniquely. But if you
in that interval,
pardon me?
map should not be invertible in that interval.
Yeah, that's my interval of interest, always. So it shouldn't be invertible in the sense that if you give me xn, I should not be able to say uniquely what n minus 1 it came from. If you can, then the matter is not chaotic. Yeah.
So you're looking at some section, right?
Pardon me?
You're looking at some biparticle section. You're not looking at
I have that in mind when I'm doing this, but it's not restricted to that. I'm just studying a map as it is.
I'm saying that the whole thing of phase space trajectory is not crossing, but how
Yeah.
if you're like not looking at a section? So
There are no longer any phase space trajectories because now the system is in discrete time and you have orbits. So x0 starts here, goes there, goes here, etc. It's discrete time. So there are no phase trajectories anymore. There are only orbits of particles.
I
Of,
get the point. Why you are looking for some special parts of the phase space?
No, it's not that I'm looking at a special part. I want to do the following. I want to illustrate to you that when you have a bounded phase space and a nonlinear evolution equation for a set of variables, then the solutions may not be computable, even though the equations are very nice, smooth, etc., provided they are nonlinear to a sufficient degree. Now, to do that with differential equations, I can only do it numerically. And then you won't know whether there is actual chaos happening or because of my time step not being small enough, or because my round off errors are too bad and I use 4th order Runge-Kutta or 27th order or whatever else. But to show you that chaos is a real phenomenon, I'm saying let's take a specific mathematical paradigm which is a discrete time map, and let's make the phase space bounded, because I want to show you that in that phase space itself information can be lost. You cannot recover the past, you cannot predict the future, and if you're given a future you can't say where it came from. That's what I want to illustrate.
So can this function be something as simple as, say, if my interval of interest is 0 to 2 pi,
Yeah.
can this function be as simple as a sin x or cos x?
Yes, of course.
that good?
Yes, of course. It can be even simpler than that, as we'll see. That's what I'm going to do. We'll take the simplest example. So let's start with that. Let's take the simplest possible example. Let's even take the infinite line and look at what happens. So, I have an x here and I have an f of x which is equal to ax plus b. I mean, nothing could be simpler than that, right? Just a line. Now, this is my line, ax plus b. And I ask, suppose this is the rule for evolution, what happens to an initial starting point? So the first thing I do is I try to solve this equation iteratively, right? Because it says xn equal to f of xn minus 1 equal to f of xn minus 2 equal to dot 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 dot. The nth iterate of x naught. That's what I want to find. And the way to do this is the so-called method of successive approximations. Even before Newton, this was known. So you start by saying, I'm going to start with the guess value x naught here. And then this is equal to f of x naught. So that's my x1. And I'm going to use that as the input and find f again. And the way to use that as input is to draw a 45-degree bisector and say, I start at this point, calculate this function. That's f of x naught, which is equal to x1. So I must use that as the input. And that's done by going horizontally to this point and calling this x1. And then go up to the graph. That's x2. So I go here and call this x2. And so on. And what's going to happen in this staircase picture? You're going to go and hit that fixed point. You're going to hit this point because at this point f of x equal to x and further iteration doesn't do anything. So you hit a fixed point of the map. This plays the role of the critical point in a continuous time dynamical system. I'm no longer going to call it a critical point, I'm going to call it a fixed point. Suppose you had started here. Well, I go there to this value, call that my next iterate, come down, go here, come down, and I'm pretty soon going to converge to this guy. Pardon? That's an attractor. Yeah, absolutely. That's an attracting fixed point. From both sides.
So independent of the initial point.
Of course, you can see that. Wherever I am in this picture, I'm going to hit that single attractor. Global attractor. So this is a flow, or rather this is a map, where there's only one fixed point, that's an attracting fixed point. Any initial condition on the real axis falls into that eventually, as time goes. It could have had the other kind of slope as well, and it could have had a negative slope as well. So here's the 45-degree line, and I have a line like this. Now what will happen is if I start here, I go to that point, I call that my new variable, come down here, go here, etc. And pretty soon I'm on this. So either I have a staircase pattern or I have a spider web pattern. In either case, I'm going to fall into this pattern. Can you think of a situation where I fall out of it? If the slope is greater than 1 in magnitude. So, first lesson in a map like this, a fixed point is stable if f prime of x at that point has a modulus less than 1. It is unstable if f prime of x is a modulus greater than 1, because then it flows away. And if it's equal to 1, what if it's exactly equal to 1? Well, either the map is degenerate or else you're going to go around exactly like you did in a center. So here's the 45-degree line. I have another 45-degree line there. That's the map. So I start at this point, I go here, I go here, I go here, I go here. I'm in a loop. Then it's neither stable nor unstable, asymptotically stable nor unstable, but it acts like a center. It's called a marginal fixed point. In the European literature, they say indifferent fixed point, but it's a marginal fixed point. Okay. So the criterion for the stability of a fixed point, stable, by that I mean asymptotically, stable if and only if not f prime at the fixed point, x star, less than. Unstable if mod f greater than. Marginal if the slope has a magnitude equal to.
This is general definition